Take a look at these numbers and try to guess what the value would be for number 4. As most of you guessed correctly, it's 12. Now let's try a more complex example. Here, we struggle to easily find the value for number 4, as the pattern is not clearly seen from the first 3 numbers. In today's video, we will try to solve this problem similar to how machine learning solves such problems. Let's go back to the first easy example and try to extract the methodology that our brain used to guess the value for number 4, which it was 12. One way to do that is by considering the numbers as x and y, plotting them on xy coordinate system, and drawing the line that touched them all. This line actually represents the linear relationship between x and y. Hence, if we extend the line to x equal to 4, it will give us the predicted value of y, which is equal to 12. Let's call this methodology find the best fit line. Now we understand how our brain finds the future values using the best fit line methodology. Let's try to use it in our complex example. Again, let's plot these points x and y in the xy coordinate system. However, this time there is no single line that touch all of the points together. We have a blue, orange, and green line, each touching 2 points out of 3. Extending the lines to x equal to 4 give us 3 options or 3 solutions. The question now is, if we get 3 different solutions, which one actually is the best fit line? To answer this, let's go back to the blue line, and let's measure the difference between the actual and the predicted value at the point that the line did not touch, the third point. The blue line predicted 4.1, but it was actually 5.9. Hence, the difference between the predicted and the actual value, which we will call it an error, is equal minus 1.8. Similarly for the orange line, which has an error equals to 0.8. And finally, for the green line, it has an error equals to minus 1.9. Now we have 3 solutions, each with its own error value. As you might have guessed correctly, our goal is to find the solution with the minimum error value, which seems to be the orange line. But is it really the solution with the minimum error? Let's take the orange line for example. What if we move the orange line slightly downwards? So it's no longer touch any point exactly, but has a small errors across all the 3 points. Let's call it the yellow line. Now we have 4 solutions, each with error values. Since the yellow line has errors at all 3 points, we cannot directly compare it with the other lines. We need a single value representing the overall error for each solution. One way to do that is to measure the error at each point for every line. For example, the blue line touched point 1 and 2, meaning it has 0 error at those points, but it has minus 1.8 error at the third point. Similarly for the other lines. But still, we don't have the single value that we can compare these 4 solutions, which one is actually the best solution. One more issue here. The minus sign in the error only shows the direction, whether we predicted higher or lower, but that's not important for our case. What we care about is how large the error is regardless of the direction. So we first square each error value to make all errors positive values. Then we might add them up together to have a single total value for each line. And for more realistic comparison, we also can take the average of the squared errors for each line again. What we have done actually here is applying one of the evaluation metrics in machine learning, which is called mean squared error, MSE. Now we can confidently say that the yellow line with an error equal to 0.16 is actually the optimal solution for our problem. So let's use the yellow line solution to predict the value for number 4. We get the predicted value of 7.1. But imagine if we had hundreds or thousands of data points. Plotting lines manually, calculating the mean squared errors for each line, and using the first method, find the best fit line, is actually impractical. Once more, let's go back to our simple example and try to extract another methodology that our brain might have used to find the answer so quickly and easily. This line, the solution for our simple example, can be described by a special characteristic, the angle between the line and the x-axis, which we will call it theta. Each line has a different theta, which means if I say a line with theta equals to x, I can draw it easily. Now, how we can measure theta? Let's draw a right triangle on the first point, 1 and 3. The vertical side of this triangle is equal to delta y. Let's call it the opposite side of theta, which is equal y2 minus y1, which is equal to 3. Similarly, for the horizontal line, the adjacent side of theta is equal to 1. Let's call it delta x. And as we know that tan theta is equal to opposite side divided by the adjacent side, hence delta y divided by delta x, that gives us a value of 3. Let's now call tan theta as w, which in machine learning we often refers to as the weight, or in this case the slope. If we calculate the value of w for all pairs of the points, we get a value of 3, as we can see for the first and the second point. Between also the second and the third point, the slope w is also 3. And between the first and the third point, the slope w is again 3. So we can confidently say multiplying w equals to 3 by the future value x equals to 4 give us y equals to 12. Here is the twist. Our assumption that only theta defines the line is not sufficient. We can draw many different lines with the same theta value, but different vertical positions. To uniquely define a line, we need one more value, the point where the line crosses the y-axis, the y-intercept, which we will call it b. In machine learning, b often represents the bias. So if we generalize the formula, instead of just w times x equals y, we add the bias wx plus b equals y. If we define the predicted value y as y hat, the final value becomes y hat equal wx plus b, which is the familiar form of a linear equation. Now we have another method that we can use to solve our complex problem. Let's call it method 2, find the best w and b. Let's try to find the value of w for our complex example using the same w formula we used earlier. For the first and the second point, w equals 0.9. For the second and third point, w equals 2.6. And the third w equals 1.75. Unfortunately, they are not the same, unlike the simple example. So what we can do now? Let's again refer back to the simple example to refine this methodology. We now know the mean squared error formula and the linear equation formula as well. So we can substitute the linear equation into the mean squared error formula. Then we can try some random values of w and b. For example, let's try w equals 0.5 and b equals to 0. Plugging in these values gives us a mean squared error equals to 29.2. Now, if we try more values of w, we can see that when w equals to 3, the MSE reaches to 0, meaning 0 error. To have a better visual understanding, let's graph the change in the MSE value for different values of w. We can clearly see that the minimum value of the curve happens at w equals to 3. Hence, without realizing it at first, our goal has always been to find the minimum value of the error function. In mathematics, finding the minimum value of any function can be achieved by finding where the derivative of that function equals to 0. Therefore, we need to find the derivative of our error function. Since it has two variables, w and b, we take the partial derivative with respect to w and b. Let me know in the comments if you would like a detailed explanation of how we take the derivative of MSE function. For now, let's plug in these simple example values into the least square estimation formulas, W and B. For W, we get the value of 3, which is exactly as we guessed. Similarly, for the partial derivative with respect to B, we get B equals to 0. So our final equation becomes y equals 3x. And this is why we get a value of y equals to 12 when x value equals to 4. Now let's apply method number 2, find the best W and B, to our complex example. Here are the formulas for W and B, representing the minimum value of the error function. Let's plug in the values from our complex example. We find W equals 1.75 and B equals 0.3667. Now, if we plug these values into our linear equation, we get y equals 1.75 times 4 plus 0.3667. Hence, the predicted value is approximately 7.4. Conclusion. Today we tried to mimic how our brain predicts future values based on patterns, which is essentially what machine learning tries to do. We found that method number 1, find the best fit line, works for simple perfect examples, but it's not practical for real-life complex data. However, method number 2, find the best W and B, based on minimizing the error function, is a general method that works even for complicated values. And this is called the least squares estimation. As a bonus tip, everything we did using method 2, least squares estimation, is exactly what happened when you add a trend line to a chart in Excel spreadsheet. When you select display equation on chart, you are actually applying the least squares estimation method behind the scenes. And as you can see, the equation shown on the chart matches the values we calculated manually. Today, we explored how our brains find patterns, how machines use errors to improve, and how we can find the best fit solutions mathematically. If you followed everything till here, congratulations. You have just understood one of the most important ideas in machine learning. In the next videos, we will explore how machines can adjust their models automatically using techniques like gradient descent. If you enjoyed this way of learning, don't forget to subscribe and join me. Stay curious and keep learning. Thank you.